Okay, today we'll be doing the 1974 Physics C free response. The question reads, the moment of inertia of a uniform solid sphere, mass m, radius r, about a diameter is 2mr squared over 5. The sphere is placed on an inclined plane angle theta as shown above and released from rest. So those are all of our knowns, the information we're given, and part A is asking us, determine the minimum coefficient of friction mu between the sphere and plane with which the sphere will roll down the incline without slipping. So if you're looking for mu and the sphere is rolling without slipping, we know that there will be angular components as well as linear components. And like I said, we know this fact simply from the statement that reads that it's rolling without slipping. When we're trying to look for friction, we know that there will be torques and forces involved. So torque falls under the angular category, and we know that if we sum up the torques, we'll have the cross product of force times radius, which is the moment arm, which is also equal to the rotational inertia multiplied by alpha, which we know is the angular acceleration, and we also know that alpha equals acceleration divided by the radius. That's just something that we know. The linear component will be the sum of the forces, and that always equals mass times acceleration. So given this, we can proceed. Let's draw a quick sketch of the angular. So if we do the diagram, I know it's small, but we just want to get a point about what's going on. Weight comes down from the center of mass, and friction is going to actually be from the bottom going up. That's friction. And between those two, we realize that even though the cross product is sine theta, because sine theta 90 minus theta will also equal cosine theta, we can make this come down and it will equal the radius times mu mg, and mu mg is force. But since it's a cross product, we also need to take into account the sine theta, which in this case is the cosine theta, just due to the complementary property. So we have r mu mg cosine theta, I'll just put that there, is equal to 2/5 m. This should be capitalized and that should be capitalized, but 2/5 m r squared times alpha. But instead of alpha, we're going to put a divided by the radius. We put that in and the radiuses cancel. So we have this, and that A is what we're going to use the sum of the forces to calculate. So this also equals mg sine theta minus mu mg cosine theta. And this is simply adding up the forces, right? So we have that, and if we solve for A, we get A equals mg sine theta minus mu mg cosine theta, all divided by mass. And these masses all cancel conveniently, and we're left with that A equals g sine theta minus mu g cosine theta. We can take this entire quantity and replace it with A, getting rid of our unknown. We have r mu mg cosine theta equals 2/5 m r multiplied by that, which is g sine theta minus mu g cosine theta. We can cancel out a lot of stuff here. This r goes out with this r, this mass goes out with this mass. We're left with mu g cosine theta equals 2/5 g sine theta minus 2/5 mu g cosine theta. All right? We can add like terms onto this side. So 2/5 plus the 1 will give us 7/5. So we have 7/5 mu g cosine theta equals 2/5 g sine theta, right? We can simply divide by 7/5 g cosine theta from both sides, leaving us with what we wanted, the mu. And the mu is therefore equal to 5 times 2 will give us 10. We just switch and we'll be left with 2/7. The 5s will cancel. So we have 2/7. And we know that sine theta divided by cosine theta is tan theta. And the gravities, when we divide, the g's will cancel. Ultimately, mu equals 2/7 tan theta. But we're not finished. There's a part B. Part B simply wants to know if mu were 0, so if this mu that we just found, if that equals 0, would the speed of the sphere at the bottom be greater, smaller, or the same as in part A? And then they want us to explain our answer. And if you think about it, if the mu were 0, no energy would be lost due to the work done by friction, because mu is the frictional coefficient. So if there is no mu, no work is lost via the work. No energy is lost via the work done by friction. Therefore, all of the gravitational potential energy would be converted to kinetic energy. And this addition to the kinetic energy would obviously result in a greater speed. Therefore, if there were no frictional coefficient, the final velocity would be increased. And we have successfully completed this free response. Thank you.